Good afternoon, everyone. Good afternoon, everyone. Hi, this is Abhishek Mathur, your physics faculty for JEE Mains. I hope you all are doing really well. I welcome all of you to this amazing section of physics. All right. So, welcome everyone. Welcome everyone. So today we are going to discuss a very interesting and amazing topic. All right, and the name of the topic is induced electric field. Basically, what we are doing right now is we have covered the first part of the chapter. We have already covered the first part of the chapter, and in this lecture, we are trying to cover the second part of the chapter. The second part will include induced electric field, self-inductance, mutual inductance, and a combination of inductors and then LR circuit. All right. So these are the topics which we are about to discuss. But uh, first, first, I hope your preparation is going well, all of you. I hope you are doing really well in your exams, and your preparation is up to the mark. All right, great everyone. It's so good to have. Uh, all right. So a brief introduction about myself. I'm Abhishek Mathur. I'm passed out from DTU and I completed my mechanical engineering from there. And I have been associated with a very renowned institute for 4 years. And right now I'm working at Altedemy, as you guys know, and I'm your physics teacher for JEE Mains. All right, great. So, this is the topic I was talking about. We are going to discuss the second part. We are going to discuss the second part of electromagnetic induction, which is really very important, and we will be, covering a lot of very important topics in today's lecture. So please watch the lecture till the end and attend the class. And you can also ask the various doubts just in case if you guys have any while attending my lecture, and you can let me know accordingly. All right, great. So here's the very first topic. Here's the very first topic of today's lecture, and the topic is induced electric field. The name of the topic is induced electric field. Great. Induced electric field. Now, what is this? What is induced electric field? What is induced electric field? See, we have seen that whenever we have a loop inside the magnetic field, and the magnetic flux associated with the loop changes. Whenever the magnetic flux associated whenever the magnetic flux associated with the loop changes, all right, we have seen that there is an induced current in the loop. There is an induced current in the loop. Great. So let me draw what we have discussed in the earlier classes. We have discussed that if I have a magnetic field like this, if I have a magnetic field like this, great. If we have a magnetic field like this, beta, and then there is a loop, there is a loop, there is a loop in the region of magnetic field, and magnetic flux and magnetic flux is changing. If if magnetic flux is changing, if magnetic flux is changing, then then i induced I induced was observed, was observed. Okay, great. Now we have also seen in the topic of magnetic force that it doesn't matter how strong the magnetic field is, it cannot apply a force on a stationary charged particle. If you remember it correctly, the formula for the force was F equals to q v cross b, q v cross b. So until and unless the charged particle has some velocity, a magnetic field cannot exert any kind of force on that charged particle. I hope this is clear to all of you. This is something which we have discussed in the previous lectures. All right. So my point here is that how can current move? How can there be current in this loop? See, what is current? What is current? Current is motion of charge particles. Motion of charge particles. Motion of charge particles. So my concern here is this: when initially there was no current, it means that the charge particles were at rest. And now when the magnetic flux is changing, we are observing that there is current in the loop. It means that initially charged particles were at rest and now the charged particles are in motion, they are moving. So my sole concern is that how can magnetic field move, can how can magnetic field make a charged particle move? All right, this is my concern, because as per this formula, until and unless a charged particle has some kind of velocity, there cannot be any magnetic force acting on that charged particle. Great. It means that magnetic field is not the reason, due to which the charged particle is moving. All right, so we must have some electric field, and that electric field is known as induced electric field. All right. Great. I hope I have made my point clear to all of you. Everyone, I hope this is clear to all of you. Great. Now we are going to write a few properties of induced electric field. Great. We are going to discuss some properties of induced electric field. All right. Induced electric field. So induced electric field is similar to our normal electric field in certain ways, and it is also different from normal electric field in certain ways. Please make a note that magnetic field magnetic field magnetic field cannot magnetic field cannot apply force force on a stationary on a stationary on a charge stationary charge particle stationary charge particle. All right. Thus 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 there must have been thus there must have been thus there must have been an electric field an electric field responsible 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 for responsible for the motion responsible for the motion of the stationary stationary charge particles. All right, stationary charge particles, because only an electric field can accelerate stationary charge particles. Magnetic field, irrespective of its magnitude, can't do this. All right. Stationary charge particle. Great. Now see some properties some properties of induced magnetic field. First, it is non-conservative. It is non-conservative. It is non-conservative in nature. Non-conservative in nature. If you remember, I hope you guys remember normal electric field. The normal electric field which we have discussed in the electrostats is conservative in nature, whereas induced electric field is non-conservative in nature. Being non-conservative in the nature means that the work done by the induced electric field depends on the path. All right, it does not depend on initial and final position, it depends on the path. Great. Second point, Second point, it is it is developed it is developed in the form of in the form of in the form of concentric in the form of concentric circles. It is developed in the form of concentric circles. Third point. Third point. It obeys. It obeys. It obeys F equals to QE. If you remember, we have discussed this point in electrostats that force acting on the charged particle is Q times. It is Q times electric field. All right. So this is the formula for force. F equals to QE, where Q is the charge of the particle, and E is the electric field. So this is something which will work here as well. All right. So there are a few similarities and certain differences between normal electric field and induced electric field. The major difference is that that particular electric field never formed closed loops, whereas it forms closed loops. See, concentric circles are what? Closed loops. All right. And it is non-conservative in nature. The normal electric field is conservative in nature. I hope this is clear to all of you. Great. Now let's talk about the magnitude. Now let's talk about the magnitude of induced electric field. Let's talk about the magnitude of induced electric field. I hope this is clear to all of you. I hope all of you have written down what I'm writing here. And great. So we are going to discuss the magnitude of induced electric field. We are going to discuss the magnitude of induced electric field. What is the magnitude? What is the magnitude of induced electric field? See, if in a region, if in a region, if in a region we have magnetic field, if in a region we have magnetic field and it is changing, and it is changing with time, and it is changing with time, we have some B as a function of time. The magnetic field is a function of time. It means that it is changing with time. All right. And then we also have a loop here. We have a loop here, right? We have a loop here, and the radius of the loop is some r. We can take the radius r. All right. And now the flux is changing. The flux is changing. Why the flux is changing, beta? Flux is changing because magnetic field is a function of time. All right. So phi equals to BA. Now the value of B will change. That's why the value of flux will also change. I hope this is clear to all of you. Great. So we know that EMF or potential difference developed is equal to d phi by dt. d phi by dt. See, the potential difference can also be written as line integral of E dot dl. Line integral of E dot dl equals to d phi by dt. Now, when we talk about d phi by dt, beta, area is constant and magnetic field is changing. So this is going to be dv by dt. So E is E, electric field is E, and dl, the loop integration of dl. The dl is a small length, all right. dl is a small length somewhere here. So when you will integrate the dl, you will get this whole circumference. You will get this whole circumference. So this is going to be what? This is going to be 2 pi r equals to this area. What is this area? Area of the loop is going to be pi r square, and dB by dt is dB by dt. So when you will solve this, pi will get cancelled from pi, 1 r will also get cancelled. So the value of E is going to be r by 2 dB by dt. R by 2 dB by dt. But this is the formula for induced. This is the formula for induced electric field. All right. And I hope it is clear to you that induced electric field is not entirely similar to the normal electric field which we have discussed in electrostats. All right. Great. So should we proceed? I think we should proceed. So this is a question. This is a question which I would like to discuss with you. We have a ring here, we have a ring here, and the magnetic field here, the magnetic field here is b naught t. Magnetic field here is b naught t. You can see that the magnetic field is not constant beta, it depends on time. Please make a note that magnetic field depends on time. And this loop is placed in a region of magnetic field. This loop is placed in a region of magnetic field, right? This loop is placed in the region of magnetic field, and and we are required to find the angular acceleration of the ring. See, this ring is non-conducting in nature. It is non-conducting, non-conducting in nature. It is non-conducting in nature. All right, it is non-conducting in nature, and its mass is m. Let me write down its mass somewhere. Its mass is m, and radius is capital R. Its mass is m, and radius is capital R. All right. Now we are required to find the angular acceleration. We are required to find the angular acceleration. All right. Great. Great. So one thing which we must know is the direction of induced electric field. The direction of induced electric field is really very important. All right. So to find that, see what we must do is that we know the direction of induced current. I hope this is clear to all of you. We know the direction of induced current. All right. The induced current flows in what direction? We can determine that by using Lenz's law. All right. We have discussed this in the previous lecture. And just in case if you have not seen that lecture, I request you to please go back and check that lecture if you have not joined our program. And I would really like to see all of you in our closed course. So please buy a closed course, and I would be really glad to see all of you in our closed course program, and we will be able to discuss a lot more things over there. All right. So what will be the direction of electric field? Direction of electric field can be simply determined by finding the direction of induced current. In this case, the magnetic field inside the loop is increasing. To reduce that, the magnetic field due to induced current should be outwards, and to produce magnetic field outwards, current should be what? Current should be anti-clockwise. It means that the current is anti-clockwise. So if current is anti-clockwise, please pay attention. If current is anti-clockwise, it means that it means that it means that if I have a positive charge here, this positive charge will move in this direction. And if I have a positive charge here, this positive charge will move in this direction. So we know the direction of force. And once we know the direction of force, we can easily determine the direction of field. It means that the induced electric field is like this. The induced electric field is anti-clockwise. Induced electric field is going to be anti-clockwise. All right. But what makes this question different? Is that the loop is non-conducting nature. Because the loop is non-conducting in nature, it means that the charged particle cannot rotate freely. All right. This has some charge q. Let me write it here. Charge q. Charge q is uniformly distributed. Charge q is uniformly distributed. All right. Charge q को हमने uniformly distribute कर दिया है. Now the charge cannot move inside the loop because the loop is non-conducting in nature. It means that every position will experience a force. This will experience a force like this. Let me draw the direction of force. There will be force. Force will act like this. Every part will experience a force, and due to this the whole loop will start rotating. The whole loop will start rotating like this. Why the loop will rotate? Because the charged particles are not free to rotate inside the loop. All right. So from here, F is equal to QE, and what is E? E is R by 2 dB by dt. And what is dB by dt? R by 2. What is dB by dt? B equals to B naught T. So dB by dt is going to be B naught. So this is force. And this force is acting tangentially. This force is acting tangentially. So the torque is going to be F into R. This is QR by 2 B naught into R. This is my torque. And can I equate this torque to I alpha? I alpha. I hope I can do that. Can I do this or not? Everyone, this can be done, all right. This is QR square by 2 B naught. And what is the value of moment of inertia? See, this is something which you should know. Otherwise, you will get stuck at this particular position, all right. So you must know the value of moment of inertia of the ring. What is the value of moment of inertia for the ring, beta? The value of moment of inertia for the ring is mr square, all right. So from r square, r square will get cancelled, and the value of alpha, is going to be what? Alpha is going to be q b naught by 2m. All right, great. So this was our first question. I hope this is clear to all of you, everyone. I hope this is clear to all of you. I hope you have understood this question really well, and there is no doubt. Is this clear to all of you, everyone? Is this clear to everyone? Do let me know, please. All right, great. Now it's time for the second question. We have to find the potential difference between points A and B. So let me first draw the diagram. So we have a circle. Whose radius is R, and the points A and B are here. This is a straight rod, and this separation is small d. This separation is small d, beta, and the points A and B are here. This is point A and this is point B. All right. So we are required to find the potential difference between point A and B if the magnetic field varies with the time as this relation. B equals to B naught T. B equals to B naught T is the variation of magnetic field with time, and we should know that when this magnetic field will vary, there will be some induced electric field, and due to which there will be potential difference. Between point A and B. Now this is something which we have to find out. All right, should we proceed? See, to solve this particular question, what we have to do is from the midpoint, we have to take an element at a separation of x. We must take an element. Of dx. I hope this is clear to all of you. And this separation, what will be this separation? If this is d, and this is x, can we find out this separation, everyone? Yes or no? Yes, we can. See, we need to find the direction of electric field, beta. The electric field will be tangential. Electric field is developed in form of circles, so at a particular point the direction of electric field will be tangential. All right. So at this point the direction of induced field is going to be what? DE. This is what? This is DE. I hope this is clear to all of you. This is E, I'm sorry. This is electric field at this particular point, right? Now, what is potential difference? If I try to find the potential difference, then the formula of potential difference is what? Delta V equals to E dot dl. Electric field dot product with length. So here, instead of dl, we are having dx. I hope this is clear to all of you. I hope this is clear to each and every one of you. Right? So when this angle is theta beta, when this angle is theta, when this angle is theta, this angle is going to be 90 minus theta. This is going to be 90. So this angle is also going to be what? This is 90 minus theta, and this is 90. This is going to be theta. This angle is also going to be theta. I hope this is clear to all of you. Everyone, do let me know if this is clear to you or not. And the value of E, and the value of E should be what? Value of E should be, value of E should be R by 2 B naught, because B naught T when differentiated with respect to time is going to be B naught, right? So this is my R. I'm taking this value as R for the time being, and R is a variable. R is a variable because this value of R will depend on the element. So it's a variable. So let's find the dot product between E and dx. Put the value of E, it's going to be R by 2 B naught, and dx is dx, and the angle is cos theta. Angle is, so this is the potential difference. This is the potential difference, but this potential difference is only for the length dx, whereas I want the potential difference between points A and B, between points A and B. All right, now to do that, what I have to do is I have to integrate. Now R by 2 cos theta can be written something. If you will look closely now, R cos theta can be written as D. This is D by 2 B naught dx. Alright, so this is dV. This is my dV. Now to find the potential difference between points A and B, I have to integrate. I have to take my element from minus L to L. Alright, if this length is D, this length is D, and this is R. This is R because this is the radius, and this is D. These two things are given. Alright, so what is this length going to be? This length is going to be under root R square minus D square from Pythagoras. Alright, for the time being, let's consider it as L. So I have to integrate it from minus L to L. So after integration, beta, this is going to be potential difference delta V, and D by 2 is constant, B naught is constant. Integration of dx is going to be x. Now I have to put the limit from minus L to L. So after integration, it is going to be D by 2 B naught 2L. From 2 will get cancelled. This is B naught T, and the value of L. What is the value of L? Under root R square minus D square. I hope this is clear to all of you. It was a pretty good question actually. I hope you guys have understood it well. Great. So this is the formula for potential difference between points A and B. I hope you have understood the process. What we have done is we have taken an element at a distance x from the midpoint of the rod, and then we found out the small potential difference between dx by taking the dot product between electric field and dx vector. Alright, dx is representing a small length. Alright, and then we have integrated from minus L to L. That's it. Great. Now we have to talk about self-inductance. This is a very important topic and a very simple as well. What is self-inductance? See, basically self-inductance and mutual inductance are something which are simply electromagnetic induction. They are simply electromagnetic induction, but there is a very small thing which you must consider here, and it is, let me draw the diagram first. If we have a coil, if we have a coil like this, if we have a coil like this, please pay attention everyone. If we have a coil like this and this is the length, this is the length, and it has n turns, it has n turns. Now what is self inductance? Please pay attention. When we have a current, when we have a current passing through the solenoid, when we have a current passing through the solenoid, we have seen that the magnetic field produced, that the magnetic field produced is given as mu naught Ni. It is mu naught Ni. Now, when we will change the value of current, when the value of current is changed, what will happen, beta? The value of magnetic field will change. B is directly proportional to I. So whenever there will be a change in the value of electric current, the corresponding magnetic field will also change. And when the corresponding magnetic field will change, can I say that? Can I say that the magnetic flux associated with these loops, the magnetic flux associated with these loops will also change? Yes or no? It will also change. So when the magnetic field is changing, magnetic flux is changing, and when magnetic flux is changing, what does we know? What do we know? What happens in that case? In that case, we have studied a phenomena which is known as electromagnetic induction. As simple as that. So basically, self-induction is nothing but electromagnetic induction only. Alright. The only change is that it is inducing an EMF in itself due to change in the current. Alright. So when when current when current passing through when current passing through the inductor the inductor will change, then then magnetic then magnetic field will change, then magnetic field will change, and thus thus magnetic flux, and thus magnetic flux associated with with the inductor with the inductor will change. All right. Now since magnetic flux has changed, EMI will come into the picture. EMI will occur. Electromagnetic induction will occur. And when electromagnetic induction will occur, there will be an induced EMF developed in this coil. Alright. And this is known as self-induction. Why does it known as self-induction? Because it is happening in the coil itself. It is happening in the coil itself due to its own current. Alright. That's why it is known as self-inductance. But essentially it is nothing but EMI. It is simply electromagnetic induction. That's it. Alright. I hope this is clear to all of you. I hope this is clear to all of you. It is essentially electromagnetic induction only. Alright. Now there's one thing which is known as coefficient of self-inductance. Let's discuss it. And if the radius of these coils is capital R, there is one assumption which we use, that R is very less than L. Right. So let's try to find the coefficient of self-inductance. See, when we talk about magnetic flux, what is magnetic flux? Magnetic flux is current into area. What is current is I. Magnetic field is mu naught Ni, and area. See, area is pi r square. Area is pi r square for one loop, but there are how many turns? N. So we must include N here. All right. Great. Amazing. Now what we can do is we can rewrite it in a different form. mu naught n. All right, this is pi r square. Now let me do one thing, let me just multiply it by L and let me just divide it by L. Then we have our n here and current here. See, when we have multiplied it by L and when we have divided it by L, what we are getting is, we are getting number of turns per unit length, n by L. What is this? N by L, number of turns per unit length. All right, this is number of turns per unit length. So the formula can be written as, mu naught n square pi r square L into I. Now again let me emphasize on one another thing, that what is this? Pi r square into L, area into length is what? It is volume. So this formula for flux, can be written as, mu naught n square volume into I. It's totally your call. Once you know the relation between capital N and small n, you can manipulate it as per your wish. All right, so what we have observed here is that pi is some constant into I, and this constant is known as L, and its value is mu naught n square into volume. This is coefficient of self inductance. This is what? Coefficient of self inductance. I hope that you guys have understood this. See, because the magnetic flux solely depends on the current, all other things are constant. Mu naught n pi r square L, all these things are constant. The flux associated with the inductor, the flux associated with this inductor depends only on the current passing through it. So all other things are constant, and we have replaced that constant by L. L is known as what? Coefficient of self-inductance. I hope this is clear to each and every one of you. This is coefficient of self-inductance, beta. All right. Now there is one thing which we must know. I hope you have written each and everything clearly. All right. So there's one thing which we must discuss, that if EMI is happening, if EMI is occurring here, then what is the formula of, induced EMF? Just give me a minute, let me just erase it quickly and then we will discuss it. All right, the formula for induced EMF, we know that EMF is what? d phi by dt. We know it from Faraday's law, that EMF equals to d phi by dt. So in this case, EMF is going to be what? It is going to be minus L di by dt, because L is constant. Great. So EMF is proportional to rate of change of current. EMF produced in the solenoid or in the inductor will depend on how rapidly or how fast or how slow the current is varying. If the current is varying slowly, then the EMF produced will be less. If the variation of current is very rapid, then the EMF produced will be very high. I hope I have made my point clear and you have clearly understood my point. All right, great. So there is one more thing which we must discuss. See, we can find the magnitude of EMF. As L di by dt. But there is one thing with which I have seen students struggle, is that what should be the polarity of the battery or the potential difference developed across the inductor when the current is changing. For example, if I say that I have an inductor like this, and and the current is increasing, and the current is increasing. If the current is increasing, what does it mean? It means that induced EMF will be formed. It means that induced EMF will be formed, and I know the magnitude of that EMF. Magnitude of the EMF is L di by dt. Now, the question which should come in your mind is that what should be the polarity of this EMF? Something like this or something like this. This is the polarity. This is something which we must know, otherwise we will be facing a lot of problem in the next question. All right, so this is the EMF, or this is the EMF. Magnitude we know, but we must also know the polarity. Right, now to understand the polarity, what we must see in the question is that whether the current is increasing or not. See, there are only two possibilities: whether this current passing through, whether this current whether this current passing through the inductor will be increasing or it will be decreasing. There is no third possibility. Either it will be decreasing or it will be increasing, or it can also be constant, but that is something which you don't have to study, because if current is constant, then there is no point of understanding self-inductance, because there will be no self-inductance. All right, so for the case of self-inductance, current either has to increase or the current has to decrease. So when the current is increasing, as per Lenz's law, what should happen? As per Lenz's law, what should happen? Will the induction want the current to be increased further, or it will oppose this change? Initially the current was less, but with the passage of time current is increasing. So as per Lenz's law, what does the Lenz's law wants? Lenz's law wants, if the current is increasing, then it must be stopped. It must be restricted. And to restrict the increase of current, this battery will work, because if I have a battery like this, because if I have a battery like this and I want it to get opposed, I will draw another battery with opposite polarity. If I will use two batteries with same polarities connected like this, then they are supporting each other. They are oh, I'm sorry, I can't write here. Basically, I want this increase to be opposed. This increase in current has to be opposed, and to oppose that, this battery should be formed. All right. So let's move towards the next question. Great. Find potential difference between points A and B. Find potential difference between points A and B. All right. So this is the question. We have an inductor. We have an inductor like this, and then there is a resistor, and then there is a battery, and then we also have another resistor, and then this is point B. This is point A, beta. This is point B. This is point A. This is point B, and this is an inductor. This is inductor, and inductor is of 2 Henry. Henry is the unit of inductance. Henry is the unit of L. Right, and this value is given to us as 2 ohm, and this is 10 volt beta. This is 10 volt, and this is also 2 ohm. And the current in the question is given to us as the current in the question, which is flowing at this very moment. The current is 10 ampere. The current flowing through this branch is 10 ampere, and it is given that current is increasing. It is given that the current is increasing at a rate of 1 ampere per second. It is given that the current is increasing at the rate of 1 ampere per second, and you are required to find the potential difference between point A and B. And to be more specific, let me ask you VA minus VB. See, when we talk about potential difference between point A and B now, we can answer VA minus VB and VB minus VA both. Alright. But in this question, I have specifically asked VA minus VB. Now we have discussed Kirchhoff's law. I will start from potential at point A, and now at this very instant you have to decide the battery formed at inductor will be like what? It should be like this or it should be like this. See, current is increasing. Since current is increasing, so as per Lenz's law, what do we want? What should happen in the phenomena of electromagnetic induction? Whether we want the current to be increased further, or do we want to oppose its cause? We want to oppose its cause. And what is the cause? That current is increasing. To oppose the increase in current, we must have a battery like this. Alright, we must have a battery like this. The value of EMF, the value of EMF is what? It is L di by dt. It is L di by dt. L is 1 and di by dt is 1. Sorry, L is 2. L is 2. L is 2. So it is going to be 2 volt. Right, 2 into 1 is 2. So when we are going from A towards B, we will encounter a battery first. We will encounter a battery first of this kind. This is wrong. Right. So we are moving from positive terminal of the battery towards negative terminal of the battery. It means that the potential is decreasing. It means that the potential is decreasing. So this is going to be plus 2 or minus 2. This is going to be minus 2. All right. And then there comes a resistor and the value of current is 10 ampere. So potential drop is going to be what? 20. And then we are encountering a battery. In this battery, please make a note of it. We are going towards negative to positive. We are going from negative to positive. It means that this is gain. This is gain of potential difference. So it should be what? It should be beta plus 10. Alright. And again we will encounter another resistance. We will encounter another resistance of 2 ohm and the current is passing through like this. And we are also moving in the direction of current. It means we are moving from high potential to low potential, and moving from high potential to low potential signifies drop of what? Minus 20, current into resistance 20, and thus we get to a point VB. So VA minus VB is going to be what? This is going to be 42 minus 10. It is going to be 32 volt. I hope you have understood this clearly. Do let me know if you have understood this or not, or if there any kind of doubt. Please clarify it. Please clarify it just in case if you have any kind of doubt. Do ask me if you have any kind of doubt, everyone. Alright, great. I hope this is clear to all of you. Now let's discuss the energy stored in the inductor. See, what happens is when we talk about inductors now, inductors are what? They are solenoids, and in between the solenoid, the air between the solenoid contains magnetic field, and the formula of that magnetic field is what? It is mu naught Ni. So whenever in a region there is magnetic field, there is some energy associated with it. So we have to look at the energy stored in the inductor. All right. So please have a look at this. If I have an inductor like this, if I have an inductor like this, draw it again. If I have an inductor like this, and there is some current, I going through it, and the coefficient of self-inductance, is L. All right. So it is L. Great. Now what happens is initially the current will be 0. Initially the current will be 0. This is something which we will discuss in detail. All right. Initially current will be 0, and then it will be maximum. Initially the current will be 0 and after some time it will be maximum I naught, right? So I am saying that the current is I. This is at some time at t equals to t. At t equals to t second, the current is I, all right, and and this current is changing. It is not constant, all right. So it is di by dt. It is di by dt. So what will happen, beta? What will happen? There will be a battery formed. There will be a battery formed, and the EMF of this battery is what? It is L di by dt. It is L di by dt. Now you must have seen. Now you must have seen the charging of the battery. In case of current electricity, this can be considered as charging of the battery. Charging of of the battery. So the power is what? Power is Vi. Power is Vi. So let me write it as this potential difference is what? It is, this is I, V is L di by dt. And what is power? Power is energy by time. Power is energy by time. So dt will get cancelled, and dE is going to be equal to Li di. Li di. Now to get the total energy, the current is increasing from 0 to I naught. When we will integrate this, we will get total energy equals to Li square by 2. And when I will put the limit of current from 0 to I naught, it is going to be what, beta? It is going to be half L I naught square. This is the formula for the energy. This is the formula for the energy stored in the inductor. All right, half L I naught square. After certain point of time, because after certain point of time, the current will assume its maximum value, that is I naught. Right? What is I naught? I naught is the maximum value of current. This is something which we will discuss in the next lecture in detail. This is maximum value of current, right? The first part of this chapter is covered in the closed course, and I would like to request you, just in case if you have not already joined, please join our closed course. You will be able to access all the video lectures there, right? So a few topics are left. Mutual inductance is left, and combination of inductor is left, and then LR circuit is left. We will be covering those topics in the next class, all right, in the closed course. So I really hope that I will be seeing most of you there, all right? So just in case if you have not scanned these two QR codes, let me just tell you what they are. The first QR code is for our Telegram channel. You can scan the QR code and join our Telegram channel, just in case if you have not joined already. And the second QR code is for the Telegram chat. Once you will, scan these two QR codes, you will be able to contact the Altedemy team, and you can get all your doubts and all your queries cleared from there. All right. So uh, please subscribe to our YouTube channel, just in case if you have not subscribed already. It really motivates us, and it really helps us to provide quality content for free of our students like you. Please subscribe. Please click on that subscribe button and show all the love which you guys have for us. All right. So this is about our course. We have more than, this is uh, full data. We have more than 140 plus lectures on our YouTube platform and our closed course platform. You can join our Altedemy channel on YouTube and access all those free lectures, and you can also join our closed course and access all the amazing homeworks and tests prepared by our expert faculties at Altedemy. The educational platform which we guys have is very convenient. You can watch all the lectures from your home. You will get all the recordings. You can watch them as per your convenience. All right, and you will get some amazing tests prepared by our expert team. The syllabus is prepared by JEE experts, those who are pioneer in their fields. All right, and we have a flipped classroom method. It means that the notes will be provided to you beforehand so that you can go through them, and when you will be coming into the class now, you won't be understanding or listening to each and everything for the first time. You will have a background story once you have gone through the notes which are provided to you beforehand. All right, and then we have doubt solving doubt solving sessions where you can get all your doubts cleared by the expert faculties. And this is how our classes work, beta. We have amazing theory prepared by the faculties. They work on their content really hard so that you guys get the best of us, and then you guys will also be getting homework materials for questions for practice so that you can practice and reinforce what we have learned in the class. All right, and just like the webinar which we are having right now, you can have a YouTube webinar. All right, and then these are the three kind of programs which we guys offer. First one is light, second one is smart, and the third one is proficient. The light program consists of interactive live classes which are held on our closed course platform, and then you will get all the homework and all the study material for the theory in case of PDFs, and there will be live test, and you will get the notes which are written in class itself. All right, but my personal favorite program which I would like you guys to have is smart program, because you guys will give one-on-one mentorship and along with live doubt solving plus regular mock test. See, mock tests are really very important in your journey for JEE Mains, and I just can't emphasize enough on the importance of mock test. So you have to give mock tests regularly so that you can get an idea of how well your preparation is going. All right, so I really hope that I will see you in our closed course. So thank you so much. I hope I will see you in the next lecture. All right. Take care. Have a good day, everyone.